Hello everybody, my name is Will. I'm going to be talking about R trees, what they are, how to use them, how to apply that. I'll just be going over a very simple explanation today, nothing too in-depth. If you're interested or curious about learning more about R trees, I'd recommend just going on the internet, searching it up. But so one of the given problems that some of you developers might face is that some systems need to search for things within a location. So you can think of this like a zip code. And if you have lots of items, like hundreds of thousands, millions, and you're checking each individually, it can be pretty slow. So we need to find a way to narrow that search area down. And in comes the solution, which is the R tree. An R tree, also known as the rectangle tree, is a data structure that can help computers skip over large areas that don't matter. So it's a faster way to look through a tree. Instead of checking every item, it groups nearby items inside a box called the rectangle, which is why it's kind of called an R tree. The rectangles form a tree of groups within groups, so boxes within boxes. As you can see in the example below there, A has the D, F, and E boxes inside of it. And then you can see right there that D, E, and F are in the box. And then D, as you can see right there, has a 1, 2 inside of it. We'll go on more a little bit in depth in a little bit here, but the worst case scenario for this would be O of N, and the average case would be O log of N. So here's an organization example. As you can see, we have the R1 box right here. As you can see, I'll try and hover my cursor around it to let you guys see it. R1, so R1 has the following boxes: R3, R4, and R5. As you can see, R3 is inside the R1 box, R4 is inside the R1 box, as well as R5. And these each have their own items inside that. So that's kind of what I mean with the R tree and having a box within a box. So another example of this is you can think of it as like a folder structure. So this is like folders within folders. So say you have multiple folders. The first folder is all businesses in the world, let's just say. And then there's another folder that limits down to northern Minnesota. And let's say we want to go to the Duluth area. We choose the Duluth folder. And then we look through the business folder in the Duluth area. So we search, we open a big rectangle, and then we only open the rectangles that overlap the area that we care about. And then we keep drilling until we find our item. So now we'll move on to implementing this inside a Python script. So in this example, what we're going to do is that we are going to create a script that will find nearby, we'll put as firms or companies, and these companies will have their own zip code and longitude and latitude. And then we'll have a find nearby firms method that will search for the nearby companies within a certain area, so like 10 kilometers. So to begin, we want to import GeoPandas and Shapely. Make sure you download that. You can either pip install that, which is probably the quickest way to do that. So first of all, we're going to create a tree. We're just going to call this demo R tree. And then we're going to define the initializing and add that to self. Oops. And then we're going to create just a little check here for us when we're start the program to help us know that the initializing demo data. Oh boy, here we come, spelling coming after me. There we go. Demo data. ... And we're just going to hard code some example data. So let's just data. Here we go. We're going to make this as a dictionary, I believe, a list of items. So do that. So we're going to have 4 firms or four companies within this list. And 1636. We're just fabricating some location data here, and this references Mankato, Minnesota. Oops, and we want to add a comma here as well. Next, we're going to do firm B. And let's see, what should the zip code be for this? 55401. How about that? I think that's Minneapolis. 449862. And then for the latitude, we'll go negative 93.2715. This should be Minneapolis. Next, firm C. And we'll go 55901. And then the 44.0670 as the longitude, and negative 92.4802 as the latitude. And this will represent Rochester, Minnesota. And then finally, for the final firm, we're going to do firm D. The zip code will be 56003, my bad. The longitude will be 44.1807. And the latitude will be negative 94.0226. And this will represent North Mankato. And now that we have that done, we need to convert this into a data frame. So this is just all going to be done on the start of the class, or the initializing of the class. So we need to convert this to a geo data frame. And I'll show you how to do that here in a second. So it'll be self.jdf refers to a geo data frame. It'll be equal to GeoPandas data frame dot geo data frame, and it'll have the data, the columns, which will represent let's see here, columns represent name, zip, latitude. Oops. Looks like I got those mixed up there. Just ignore me, okay, guys? And longitude. And then we are going to want to do the geometry. Geometry, guys. Geometry. This should be equal to GPD dot points from XY D3 4D in data. Oh boy, this is a long one. Sorry, guys. And then, sorry, just looking at my notes here. D2 4D in data. Yep, that looks right. Okay. Sorry, guys. Here, how about, in order to make this a little bit easier to see, let's go like this. Geometry, because GPD data points. And then finally, we want to do this CRS equals EPSG 4326. And that just does the latitude and longitude. And then we close it. Next, we just want to print a little check for us, just for us to see the original latitude and longitude. Sorry about that. So, moving on. Sorry, I was just fixing some errors. Moving on, we want to project the EPSG for the distance calculations. So what we're going to do is self.gdf equals self.gdf dot 2 underscore CRS EPSG equals 3857. Then we want to trigger the arbitrary build. This is just done automatically when you call the assignDex function. So we just do equals self dot gdf dot assignDex. We'll print out another statement just for verification here. Print spatial index tree created. And then next, what we're going to do is we're going to define the find nearby firms. So what we're going to do, this is the method we're going to use to find nearby firms. So self, zip code as an argument, and then we want to just have the radius, to change this, radius in kilometers, we'll do it to like 10. Next, do a print statement to help us verify. Printf, searching for firms near zip, then we'll enter the zip code, within, then we'll enter the radius, next, what we're going to do is find the target location. And then, so the target will equal self.gdf and then we'll have that be the zip. Equals zip code. And if that target is empty, target.empty, then print the zip code's not found. And then return none. After that, we are going to want to change the target point. Go to the zero, geometry. And we want to print that we print the target points just for verification, just to show you guys. Then we want to create that circular buffer around the search area around the zip code. So we're going to create that here. Buffer equals target underscore point dot buffer. Make that radius equal to radius in kilometers times 1,000. And then after that, we want to create the print statement. Next, want to use the archery to find the intersection, so anything that's in that buffer we want to return. So what we'll do is write nearby equals self.gdf. And then we'll print the found ones. So printf. And then what we're going to want to do is just return the nearby firm's name and zip. And then now we'll set the equal domain. We'll create the demo object. We'll set this results variable equal to what we get, equal to what we return by firms. And let's start with just Mankato, just to show you. We'll have it hopefully return North Mankato. We'll have this set this to 50 for right now. And then we'll print them out. And we'll see what we get. So, let's run this. Oh. Alrighty, and just got that fixed. So these are the four original firms right here: firm A, firm B, firm C, firm D. Firm A is Mankato, firm D is North Mankato, firm B is in Minneapolis, and firm C is in Rochester. So we want to find the firms that are closest to Mankato, 50 kilometers. So what we did, created the spatial index, searching for firms near zip 5600.1 within 50 kilometers. We found a target point. We search the buffer within that. When we find two nearby firms, we find the business in Mankato, and we find the business in North Mankato. So that's kind of how it works. Thank you.